Hi everybody! So in today's video we're going to be looking at some of the things that derivatives can help us do. So we've learned a lot about how to find a derivative and now we're looking at a few of the applications. The first application we're going to look at is L'Hopital's rule. So if you think back to what we remember from our limits unit, if I had given you this problem in the limits unit, we would have said that our first step would be to try to plug this in. If I try to plug in -2, on the bottom I get 0. One thing that we didn't talk too much about is that we actually get 0 on the top as well. So on the top we would have 4 minus 6 plus 2, which is also 0, which means the answer would be 0 over 0. Now this is something called an indeterminate form, which we're going to talk more about in 1 second, but we didn't talk too much about that before, so I wanted to point that out. What we would do then, because we couldn't plug in our number, is we would factor. So we would have the limit as x approaches -2, and on the top we would have x plus 2 times x plus 1 over x plus 2. We would see that these factors canceled, and we would have the limit as x approaches -2 of x plus 1. And then we would retry plugging in our number, which when we tried that, we would get -1 as our answer. Another problem we should review from our limits chapter is this one. Again, if you try plugging in 0, there's a 0 in the denominator. And one thing we didn't talk too much about was that there's also a 0 in the numerator, because you would have 1 plus 0, which is the square root of 1, minus 1, which is 0. This is again called an indeterminate form. So to fix that problem, what we would usually do is multiply by the conjugate. So we would get the limit as x approaches 0 of the square root of 1 plus x minus 1 all over x, and we would multiply by the square root of 1 plus x plus 1 over the square root of 1 plus x plus 1. Which means when we multiply out the top, which we don't really have to write all that out because we know that this is going to happen, the square roots go away and you just get 1 plus x minus 1 times 1, which is 1. And on the bottom we said don't multiply this out, just leave it alone. Now on the top the 1's would cancel, and so then we would have the limit as x approaches 0 of x over x parentheses square root of 1 plus x plus 1. Now these two x's cancel, and so we would get the limit as x approaches 0 of 1 over the square root of 1 plus x plus 1. And now if we retried plugging in our 0, we would have 1 over 2. What we're going to look at today is another option for figuring out the value of these limits. So what L'Hopital's rule, and by the way, L'Hopital is the French word for hospital. It was also this guy's last name. So this is literally saying that when your limits don't work, send them to the hospital. If you try plugging in your number to a limit and you get either 0 over 0 or infinity over infinity, we call these indeterminate forms. And if you get an indeterminate form, then rather than going through all of this algebra, you could take the derivative of the numerator and take the derivative of the denominator separately. So you're not doing quotient rule, you're just doing the top separately from the bottom, and then try your limit again. You can actually repeat this process every time you get an indeterminate form until your limit works. So let's look at an example. If I said what is the limit as x approaches 0 of sine of x over x, if I try plugging in my number, I get 0 over 0 because the sine of 0 is 0, and if I plug it into the bottom, I just get 0. This is an indeterminate form, which means I can apply L'Hopital's rule. So L'Hopital's says take the derivative of the top, which the derivative of sine is cosine, and then take the derivative of the bottom. The derivative of x is 1. And now try plugging in your number again. So if I do cosine of 0, I get 1 over 1, which is just 1. And that's the answer to your limit question. Now this can actually help us with some of the problems that we used to have to do a lot of algebra before. So we're actually going to do these two problems again, but we're going to do it using L'Hopital's rule. So for this problem, we know that if we plug in -2, we get 0 over 0, because we tried that up above here. So if we take the derivative of the top, the derivative of the top would be 2x plus 3, and if we take the derivative of the bottom, we just get 1. Now if you try plugging in your -2 again, you get -4 plus 3 over 1, which would be -1. And that's your answer. You'll notice that that matches the answer we got here using all of our algebraic techniques. So we're getting the same answer, we're just using derivatives to get that answer. For problem number 2, we know we get 0 over 0 because we tried it earlier. So now if we take the derivative on the top, the derivative here, we're doing the derivative of 1 plus x to the 1/2. So I would have 1/2 times 1 plus x to the -1/2 times the chain, and the chain would just be 1. And then the derivative of -1 is 0. On the bottom, I would just have 1. So if I try to simplify this a little bit, I'm just thinking that plugging in 0 right now would be a little bit tough because of this fraction within a fraction thing. This having a divided by 1 doesn't really matter, and this 1 doesn't really matter. So before I plug in my 0, I'm going to rewrite this like this. Now if I plug in 0, I get 1 over 2, which you'll notice is the same answer I got here. I just did this one without having to go through all that conjugate stuff. Let's take a look at a couple examples where in the past we wouldn't have known what to do because there is no algebra that will help us. So if I look at number 3, I can't really plug in pi over 2 because secant, which is 1 over cosine, just as a brief review, if I plug in pi over 2, I get 1 over 0. So that's going to be undefined. If we think about the graph, it actually approaches infinity there. And on the bottom, as tangent approaches pi over 2, it is also infinity. So you would have infinity on the bottom as well. Those are undefined values for those functions. On the graphs, you get a bunch of asymptotes. So if you get infinity over infinity, that is also an indeterminate form, which means that you can actually use L'Hopital's rule to find the limit. So I would have the limit as x approaches pi over 2. The derivative of secant would be secant times tangent. And on the bottom, the derivative of 1 is 0, and the derivative of tangent is secant squared. Now that means one of these secants will cancel. So I'm going to get tangent over secant. Now, I can try plugging in pi over 2 again, but you're going to notice I'm going to get infinity over infinity again. So I'm actually going to try a little bit of algebraing here by rewriting this in a slightly different way. Instead of writing tangent, I'm going to write this as sine over cosine. And instead of writing secant, I'm going to write 1 over cosine. And I'm going to do that because it helps me see that these cosines cancel. So my new limit would be just sine. Now, the sine of pi over 2 I can easily evaluate. It's just 1. So L'Hopital's rule took a limit I couldn't do, and it made it so that I turned it into something easy to simplify so I could do that limit. If I look at number 4 and I try plugging in infinity, I'm going to get infinity over infinity again, which is an indeterminate form. So L'Hopital's rule says, hey, that's okay. Just take the limit on the top, the derivative on the top. Now the derivative of e to the something would be e to the something times the chain, which is 2, and take the derivative on the bottom, which is 4x. Now this is going to simplify a little bit. The 2 and the 4 are going to simplify and just make a 2. So I'm going to have the limit as x approaches infinity of e to the 2x over 2. Oh, x. There we go. Once again, if I try plugging in infinity, I get infinity over infinity again. And unlike this problem, where doing a little bit of algebra fixed this for me, there's nothing to really algebra here. Like I can't say e to the 2x is really equal to something else like I could with tangent. So instead, I'm just going to apply L'Hopital's rule again, which means I'm going to take the derivative here again. The derivative of e to the 2x is e to the 2x times 2, and the derivative of 2x is just 2. So these 2's cancel, and I get the limit as x approaches infinity of just e to the 2x, which if you plug in infinity is just infinity. And that would be your answer. Now, a couple things that you should note. Just because we can use L'Hopital's rule doesn't always mean that we should. So in this example, if you were to try plugging in infinity, you would get infinity on the top and infinity on the bottom, which means you could use L'Hopital's rule. To do that, you would take the derivative on the top, which would be 12x squared plus 10x minus 6 over 12x cubed plus 18x squared minus 14x. Now if you try plugging in infinity again, once again you would get infinity over infinity, so you would try L'Hopital's rule again, which would give you 24x plus 10 over 36x squared plus 36x minus 14. Once again, if you try plugging in infinity, you would get infinity over infinity again, in which case you would get the limit, you're doing L'Hopital's again, of 24 over 72x plus 36. And now if you try plugging in infinity, you get 24 over infinity. And one of the things that we said earlier this year is if you have 24 pizzas shared with infinity of your friends, that's just 0. So L'Hopital's rule works, it gives you 0. But let's check out option 2. Option 2 is just remember some rules for limits. We said that when x is approaching infinity, you only look at the highest powers. So the highest power on the top would be 4x cubed, and the highest power on the bottom would be 3x to the fourth. The simplified version of that would be 4 over 3x. So we would use that to find our limit. Now if you plug in infinity, you get 4 divided by infinity, which again we said was 0. I think this is faster. You could do this, but it's tedious, and if you just remember some of your limit rules and you look at the highest powers, you don't have to do all that work. One mistake I do want you to know to avoid is this. In this problem, if we plug in 3, we get 1 over 0. A lot of students will be really over-enthusiastic about L'Hopital's rule, and they'll think, oh, just take the derivative of the top and the derivative of the bottom. But L'Hopital's rule can only be applied when you have 0 over 0 or infinity over infinity. Since we don't have 0 over 0, we have 1 over 0, you cannot apply L'Hopital's here. Instead, you have to think back to what we talked about with limits. If there's nothing to algebra and your number still can't be plugged in, then that means there must have been an asymptote. So in this case, there would be an asymptote at 3. Since the top number is positive and the bottom is an odd power, it would have gone down and then up, which means the limit does not exist. If you apply L'Hopital's rule, you would have the limit as x approaches 3 of 0 over 1, which is just 0, which is actually the wrong answer. So it's not just that you can't apply it, it's that if you do try applying L'Hopital's rule, you literally get the wrong answer. All right, thank you guys so much for watching, and I'll see you for some practice.